Thank you, Yair. Well, it is a great honor to be talking here in honor of, on this occasion. And as Yair said, Mostow's work, especially in my field, Mostow rigidity, is an absolute bedrock principle. And one of the amazing things about this result is that it's not just the statement of the result, which is important, although the statement is of enormous consequence, but it's every idea in the proof is important. And so it's my great pleasure to start this lecture by talking about just one special instance, but one of the most important instances of Mostow's rigidity theorem. So this talk will be in two parts. I'm going to start talking about real hyperbolic three manifolds, and then there'll be a second part about complex hyperbolic manifolds, which will raise some different issues, and I'll describe some current research topics there. I'll also try to draw attention to some open problems that remain in this very active field. Okay, so this development subsequent to Mostow's work, and to a certain extent prior, that I'm going to discuss, the main players are Alfors, Sullivan, Gromov, and Thurston. So let me start with Mostow's proof of Mostow rigidity. So here's the statement of the special case I'm interested in. I still find this case amazing every time I think about it. If you have two compact hyperbolic three manifolds, that is, closed three manifolds with metrics of constant negative curvature, if a purely combinatorial invariant, their fundamental group, if their fundamental groups are isomorphic as groups, then the manifolds are isometric as manifolds. So for example, the volume of the manifold becomes a topological invariant. So here's the proof. Step one. So these spaces are k pi 1. So if you have an isomorphism between their fundamental groups, you can realize it by a homotopy equivalence between the manifolds. So let F be such a map. And then lift to the universal cover. So the universal cover is the three ball endowed with the hyperbolic metric in both cases. Now the three ball has hyperbolic geometry, so here's a typical geodesic. And the first beautiful idea in the proof is that the image of this pristine geometric object under this sloppy homotopy equivalence becomes a quasi-geodesic, which is in fact close to being a hyperbolic geodesic. It tracks a unique hyperbolic geodesic. So even though this map respected in no ways the Riemannian metrics on domain and range, its lift to the universal cover is trying its best to preserve hyperbolic geometry, at least up to a bounded factor. The second step, which I think is one of the most profound, is the following. The fundamental group of M is acting freely permuting fundamental domains in this ball, but the action extends to the sphere at infinity, the natural boundary of hyperbolic space, and there the action is very complex. It doesn't have any fundamental domains. In fact, it's ergodic. It's ergodic on the set of pairs. And one can extend this lifted map from the ball to the boundary of the ball. And in the boundary of the ball, it gives a conjugacy between these two very complex and chaotic dynamical systems. So that's the first point, is that the action of the group on the sphere on this side is conjugate topologically to the action on this side by the boundary values of F. Now, even better, the fact that these geodesics map to crinkly geodesics means that the shadow of a ball in the first hyperbolic space, the shadow on the sphere at infinity of a ball, which is round, maps to something that's an approximately round shadow. And that means that the boundary values of this map are what are called quasi-conformal maps. So let me just remind you that if you have an isometry of hyperbolic 3 space, it induces a conformal map of the boundary. That is a Mobius transformation. If the boundary values were conformal, then the boundary values of F would extend to an isometry that would conjugate one group to the other, and that would end the proof. It would prove that the two manifolds are isometric. And what you get sort of for free is that the boundary values are quasi-conformal. They're off by a bounded amount of distortion. That brings us to step 2. How can we analyze this quasi-conformal map? And the beautiful fact is, as I just mentioned, if F were conformal, we would be done. Otherwise, there's something kind of strange happening. You have an invariant complex structure on the target sphere, and you have an invariant complex structure on the domain sphere. So you can take the target complex structure and pull it back. And the round circles in the target, if the map is not conformal, pull back to ellipses in the domain of the map. If these were round, the map would be conformal, but otherwise it has to really be distorting the complex structure. And then you can record this distortion by just drawing the major axis of the ellipse. And because F is a conjugacy, that family of lines, one line in each tangent space of the sphere, is invariant under the action of the group. So to complete the proof, we now just have to show that that's impossible. That is, there's no way to coherently choose a line in each tangent space of the two-sphere, so it's invariant under the action of this big group. Okay, and at that point, the map F passes out of the picture, and this is this beautiful insight that we can use ergodic theory on the sphere at infinity. And I should mention that this line field is only measurable. And it's a beautiful fact that we start a beautiful mathematical ansatz that we begin with a purely topological discussion, and we're driven to actually use not entirely unsubtle results in measure theory to complete the proof. So here's the completion of the proof. So suppose we had an invariant family of lines on the two-sphere. I've drawn a tiny patch of it here. Well, according to the Lebesgue density theorem, if you have a measurable family of lines, then at most points, at a very small scale, most of the lines are pointing in the same direction. But now we have this huge group of hyperbolic isometries that's leaving this line field invariant. So we can take a region where the lines are nearly parallel and blow it up by a sequence of group elements. That doesn't change the line field, but it takes the region where it was nearly parallel and it transforms it to a larger region. And so what we're able to conclude by applying the dynamics is that in fact the line field looks like parallel lines in a standard Euclidean chart. So it appears that we have a family of parallel lines on the complex plane, say, that's invariant under the action of this group. But such a family of lines, when viewed on the sphere, looks like circles all tangent to the point at infinity. So if you have a group action that leaves this family of lines invariant, all the elements of the group have to fix this one special point. And obviously that's impossible for a co-compact group. OK, so there's many ideas in this proof that have been used over and over again throughout geometry and dynamics. So just to give you a hint of the fecundity of this argument, let me just mention one or two further developments. So a lot of work has been done by investigating what happens when the group, rather than being co-compact, is simply discrete and finitely generated. Another way to say this geometrically is we consider a general hyperbolic manifold or even orbifold. It should be complete, but no restrictions on its volume. And such an object, the quotient 3 manifold might look something like this. It might have a cusp. It might have some infinite volume flaring ends that are cut off by surfaces. It might have some weird ends that hopefully look like the product of a surface with an interval. That's what the quotient manifold looks like. When we go to the action on the sphere, what happens is the action is no longer chaotic necessarily on the whole sphere. There may be some regions where the action has fundamental domain. Those are these circles here. And then there's this chaotic locus left over. This is called the limit set of the group. So we have a much richer class of dynamical pictures that arise when we go to infinite volume. And nevertheless, the analog of Mostow rigidity goes through in this setting. So the first result I'd like to mention is Sullivan showed that there's a relative version of Mostow rigidity. Namely, if you simply have a finitely generated discrete group, then there's no invariant line field on its limit set. And that has tremendous consequences for the theory of hyperbolic 3 manifolds. It basically means the different possible shapes of a given hyperbolic manifold are parameterized by the Riemann surfaces at infinity. So the Teichmüller theory of the boundary controls the Teichmuller theory of the three-manifold. In this way, one sometimes says, the theory of three manifolds is superficial. It's all going on the boundary. And if there's no boundary, then it's rigid. A second big development along the same lines, there's an important conjecture formulated by Thurston, the ending lamination conjecture, also the tameness conjecture, and finally, with work of many people, Brock, Canary, Minsky, Egal, and Caligari-Gabay, we now have a complete understanding of what all possible hyperbolic three manifolds with finitely generated groups look like. That is, there's a complete set of invariants which classifies them. There's a topological and combinatorial invariant, which is roughly the shape of the three manifold. And then there's these Riemann surfaces at infinity. They range in finite dimensional Teichmuller spaces, which are well understood. So we now understand all finitely generated groups that are discrete and act on hyperbolic three space. And a particular consequence of this, which is a long-standing problem, goes back to the 1960s, is the so-called Alfors measure zero conjecture, which says the only way the limit set can have positive area is if it's the whole sphere. But this is only the tip of the iceberg. These are results in the area of hyperbolic three manifolds per se. So there's a tremendous number of other mathematical developments that issue from Mostow's work and Mostow's proof. So for example, this simple idea that a geodesic goes to a quasi-geodesic was abstracted by Gromov, leading to the definition of hyperbolic groups. Hyperbolic groups are groups that have the combinatorial properties of groups acting on hyperbolic space, and in particular, they have quasi-geodesics that are stable. Gromov also contributed a beautiful idea for doing the proof of Mostow rigidity without using ergodic theory. And this idea leverages the fact that there is a unique tetrahedron, ideal tetrahedron of maximum volume in hyperbolic three space. And it sort of explains why Mostow rigidity fails in dimension 2, because all ideal triangles are isometric, but not all ideal tetrahedra are. There's a cross ratio of 4 points on the sphere. So that's only the beginning of yet another offshoot of this development. One more that my thesis advisor, Dennis Sullivan, pursued with great success is the integration of Mostow's argument into complex dynamics, and especially into the theory of renormalization. So this picture, which I won't explain in detail, represents a very simple bifurcation pattern in a family of one-dimensional dynamical systems. So we're doing some iteration on the real line. There's an attractor. As we increase the parameter, it bifurcates into a cycle of order 2, then 4, then 8, and then there's this limiting Cantor set here. And there's all sorts of beautiful self-similarities in this picture. For example, this little bit up here, when blown up, looks like a rescaled version of the entire picture. That's qualitative, but even better, the rate at which these period doublings occur, this apparent self-similarity around this special Cantor set point, is a universal number. It's the same in all of these windows, and it's the same in all one-dimensional families. And this is now explained by first passing to the complex plane. And now here we have a complex dynamical system with a limit set. My pointer is with a limit set, which is the black part. and now we play the Mostow argument, that is, we start zooming in on this black set, and it becomes more and more ubiquitous. And the point is, this is the area where the dynamics is destroying any invariant line field. And so we don't quite obtain rigidity, but we obtain asymptotic rigidity. And that's exactly where the existence and uniqueness of fixed points of renormalization comes from. There's other versions, such as the golden mean Siegel disk, whose boundary is shown here. When you blow this up, it's self-similar with some universal factor around the center of our picture here. Those are all instances of methods in a broader field now called conformal dynamics, which turn on the same motifs that appear in Mostow's proof. OK, so let me mention an open problem. One of my favorite open problems in complex dynamics. The problem is to really generalize Mostow's theorem or Sullivan's theorem from groups acting on the sphere to rational maps acting on the sphere. So here's the problem. Suppose you have a rational map on the Riemann sphere, that is a ratio of two polynomials of, let's say, of degree 1 or 2 or more. It has something called the Julia set, which up to measure 0 is just the closure of the periodic points. That's the analog of the limit set. And the question is, the problem is to show there is no invariant line field on the Julia set of F. And this is open even in the case when the Julia set is the whole 2 sphere, which is roughly like the co-compact case for Kleinian groups. One reason this might be slightly harder than, well, there's several reasons why this seems to be slightly harder than the original proof for Kleinian groups, that is for hyperbolic 3 manifolds. One is that, of course, a rational map on the sphere has critical points, so it's much more nonlinear than the elements of a Kleinian group. The other one is that this conjecture is false. So it turns out that the addition law for the Weierstrass P function gives rise to a very special rational map on the sphere. And that if this rational map is associated to the Weierstrass P function for an elliptic curve, and if you draw the family of parallel lines for that elliptic curve upstairs in the complex plane and let them descend to the Riemann sphere, so think of the elliptic curve as a twofold branch cover of the sphere with the P function as the map, that gives an invariant line field for the addition law. And so any proof of this theorem is going to have to single out these addition law examples as special cases. And for example, Thurston proved a very special but interesting version of this theorem where the critical points of F are pre-periodic, and his proof exactly does pick out these special cases. Well, as long as I'm mentioning Thurston, I can't say Mostow rigidity without mentioning Thurston, at least in the case of dimension 3, because what Thurston showed is that most 3 manifolds are hyperbolic. That is, most 3 manifolds do carry a metric of constant negative curvature. So we have existence, and then we have uniqueness by Mostow. That's a very rigid situation, and it means, for example, that volume is a very good topological invariant. If you want to tell 2 3 manifolds apart, one way to do it is to compute the hyperbolic structure on them, compute the volume. If the volumes do not agree, then the manifolds are not isomorphic. Now notice that we're in an odd dimension. So the volume is not given by a Gauss-Bonnet formula. After all, the Euler characteristic will be 0. The volume is probably some transcendental number. It can be written down often in terms of the Lobachevsky function. But in practical terms, it turns out to be an excellent invariant. And for example, there was a long history, of which I'm giving you a glimpse, of the classification of knots. It's now possible to classify all knots up to 16 crossings, of which there's more than 1 million, simply using volume and mild modifications thereof as a way to tell them apart. So there's been a tremendous impact on the theory of 3 manifolds by the fact that rigidity holds for these canonical metrics. In some sense, the combination of Mostow and Thurston is a fitting sequel to the uniformization theorem proved at the turn of the last century. That was a 2-dimensional theorem for Riemann surfaces, and now we have a topological 3-dimensional theorem that's very similar. And of course, I should mention that although Thurston did the case of knots, the completely general version of this theorem is due to Perelman. Okay, so that's a glimpse of the central role of Mostow rigidity in the theory of 3 manifolds. Let me turn to my second topic, which will pick up on this theme that volume is useful. So I would like to talk about the use of complex hyperbolic volume, no longer real hyperbolic volume, as a tool in the study of moduli spaces. And this discussion I'm going to present, it was prompted by a recent preprint of Capes and Müller, but it goes back to some work of Thurston in 1998. some work of Dan and Mostow prior to that. And finally, a beautiful and not very well remembered paper by Alan Durfer and Vey in 1943. Okay, so let me try to set the stage for this discussion. So I'd like to apply rigidity, volume computations, etc., in the setting of moduli spaces. Now, what moduli spaces am I going to consider? I'd like to consider one of the simplest, which is the moduli space of n distinct points on the sphere. And these points are labeled. They're numbered, b1 up to bn. So this is just a manifold. It's a list of n points modulo the diagonal action of the automorphism group of the Riemann sphere. So this manifold is usually called M0n. It's Riemann surfaces of genus 0, of which there's only one, with n marked points on it. Now, before we discuss volume, let's discuss Euler characteristic. And you might be anticipating that since we're in even dimensions now, since we're talking about complex manifolds, volume is not going to be an interesting invariant, because volume should be proportional to Euler characteristic in this setting. So let me first compute the Euler characteristic of this moduli space, because it's not very hard. So there's a forgetful map. If you have n marked points, then you can just throw away the last one. Then you have n minus 1 marked points. And that presents moduli space as a fiber bundle over a moduli space of smaller dimension. And the fiber is just a surface of genus 0 with n minus 1 points removed. So punctured at n minus 1 points. If you've chosen n minus 1 points, you're not allowed to pick those for your nth point. So you throw away those points, and then you pick a point in their complement. And well, I know how to compute the Euler characteristic of the n minus 1 sign punctured sphere. And so by induction, you compute that the Euler characteristic of moduli space is a factorial. It's up to sign. It's simply n minus 3 factorial, where n is the number of points. OK, so now shall we compute the volume of moduli space using Gauss-Bonnet? Well, yes and no. So first, let me tell you the no part. Moduli spaces are not hyperbolic. So much as I might like to compute the complex hyperbolic volume of this manifold, it does not have a complex hyperbolic structure that's compatible with the complex structure that that's already God-given. So the moduli space of 5 or more points is never isomorphic to a quotient of complex hyperbolic space, unfortunately. So it's not, in this setting, Thurston's theorem is false. There's plenty of manifolds that have the topological features of complex hyperbolic manifolds, but don't carry complex hyperbolic metrics. That's very rare, in fact, for complex manifolds. And one of the reasons we know this is that there's a beautiful theorem of Royden. You see, if moduli space were complex hyperbolic, then its universal cover would be this beautiful symmetric space. They would be just a ball in Cn. It would have a huge automorphism group, even as a complex manifold. But Royden showed that, in fact, the universal cover of moduli space has a discrete group of automorphisms. In fact, the automorphisms just come from the mapping class group of the n times punctured sphere. That is, roughly, they come from the braid group. And consequently, there's no homogeneity to the universal cover. In fact, the universal cover is as inhomogeneous as possible. So my original question is foundering, but just for a moment. OK, so now let me continue and discuss a way of thinking about the moduli space of n points on the sphere. So suppose you're just given n points on the sphere. What kind of geometry might underlie this configuration? So here's a beautiful idea. Let's add more data to the picture. So we're going to fix some weights on our n points. The weights will be between 0 and 1, and the sum of the weights will be 2. And then what I want to point out is the following. If you have these weights plus actual locations for n points on the sphere, well, then you have a naturally determined meromorphic 1 form on the sphere. Namely, you put a pole of weight mu I at the ith point, and then you just take the product. So there's a meromorphic one form with poles along these points bi, notice that the divisor of this form, which would be the, there should be a minus sign here, the sum of these mu i's times the bi's, it has degree 2, as should any anti-canonical divisor on the sphere. And so that's a lot of interesting additional data. The only problem, yeah? No, because there are no integers between 0 and 1. So, yeah, so one of the problems, but it's not a big problem, and it wasn't a problem in the 19th century, by the way. You would just write this down and say, there's a meromorphic function, and now let's integrate it and do whatever we want with it. But of course, this is a multi-valued function as I presented it. However, its absolute value is perfectly well defined. And it's, when you put an absolute value signs in, it then becomes a metric, because the absolute value of dx is a conformal metric. It's a way to measure distances on the sphere that's compatible with the angles. So forget, think of this as 19th century, and this is 20th century. So in the 20th century, you observe that this data determines a metric on the sphere. And because of the fact that this omega is holomorphic away from these poles, the metric it determines is flat. So you have a flat metric on the sphere with some sort of singularities at these endpoints. And in fact, this metric turns out to be isometric to a convex polyhedron in R3. And the cone angles at these bi's are related in a simple way to the values of these mu I. So for example, if you take 12 points on the sphere, then you can set all of the mu i's equal to 1/6. And if you take the points in a very symmetric configuration, the corresponding Riemann surface plus metric is isometric to the regular dodecahedron. Okay, so we haven't changed our moduli space, we've just changed how to think about it. So we can think of this moduli space with more data, these weights, as parameterizing these different possible shapes of polyhedra. So you should imagine this dodecahedron, which happens to be very static, as having some deformations. You can start sliding the vertices around, continue to take their convex hull in R3, and you'll get a whole family of convex shapes. And if you do it just right, you can keep the cone angles the same. And that's what this moduli space is now parameterizing. It's a moduli space of polyhedra. And oddly enough, when you add this perspective to moduli space, it becomes a complex hyperbolic manifold after all. So here's the statement. So first, as I just said, we can think of this moduli space with these mu's now as a space of metrics with given cone angles. And the theorem is that moduli space is now naturally a hyperbolic manifold. And in fact, the periods of this form, which are multi-valued functions, at least locally define maps from this moduli space into the corresponding complex hyperbolic space. OK, so let me give you some background on this result. So this kind of result, in slightly different language, was known to Schwartz and Picard, and it was developed very completely by Dan and Mostow, who used it to construct some amazing examples of lattices in SU21 and SU31, which we'll come to. And then, to my mind, this development reached its apex with the 1986 Math Olympiad. So in the 1986 Math Olympiad, there was a problem having to do with a pentagon and a little game people played, and they had weights on the pentagon, and you'd lend money to your neighbors. And one semester at Princeton, Thurston was teaching his graduate course, and there was no syllabus for the course. And a week before the course was to start, he was having lunch with people, and somebody said, why don't you talk about problems like this Math Olympiad problem? And so he started talking about this Math Olympiad problem. And by the end of the course, he had rediscovered the constructions of Dan and Mostow from an entirely geometric perspective and taken them somewhat farther. So let me tell you what Thurston's result is. I'll tell it to you in the case of this specific set of weights. So let me just see if I'm... sorry. So what I want to do here is explain, what I want to do here, let me explain how this moduli space becomes complex hyperbolic. So let me do it with this specific set of weights, and then we'll come to Thurston's exact statement. So how can you put a complex hyperbolic structure on the space of polyhedra with these weights? So a particular case is something that's almost a pentagon. So you make the angles proportional to 7, 7, 7, and 8. That gives you a convex body, a convex polygon. If you double that polygon, you get a flat metric on the sphere with the desired cone angles. And what we want to do is map the space of such configurations of 5 points interpreted as polygons into complex hyperbolic 2 space. Let me just explain how this can be done. So here's a nice idea. If you have 5 points on a sphere, you can associate to those 5 points a Riemann surface of genus 25, canonically. How? Well, I'm using there's many possible constructions. I'm using the fact that the denominator here is 18 to make the sum come out to be 2. So what you do is you take the 18-fold cover of the sphere branched over those points. So I put one of the points at infinity, and then I have a Riemann surface that's described by this very simple affine equation, a generalization of a hyperelliptic curve. It's an 18-fold cover of the sphere branched over 5 points. Now, of course, this Riemann surface has a lot of symmetry. In particular, the group Z mod 18 acts on this surface, and it acts on its homology. The action of Z mod 18 on its homology is a purely topological thing. It doesn't depend on where the points are. If we just think of the complex homology, it's sort of fixed once and for all. The model for that doesn't depend on where the points are located. However, there is something that does depend on where the points are located, namely the cohomology class represented by our form. So now I'm answering Pavel's question. If we take our form omega can now be written as dx over y to the 7th. See, y is a multi-valued function on the Riemann sphere. On x, it becomes single-valued. And this is now our holomorphic form, rectified via Riemann's trick to become a single-valued holomorphic 1 form on a Riemann surface spread over the sphere. And so whenever we have a configuration of points, we have a canonical line in the complex homology of the sphere. But remember, there's this Z mod 18 action, and it's not just in an arbitrary piece of this homology. You can decompose this homology according to the eigenspaces of this Z mod 18, and this lies in the eigenspace associated to one of the 18th roots of unity, namely the minus 7 times the primitive 18th roots of unity, because we have a y to the 7 in the denominator here. OK, so now here's an interesting problem in its own right. When you have Z mod 18 acting on the homology of this Riemann surface, the Riemann surface has a canonical inner product on its homology, coming from intersections of curves, purely topological. That turns the complex cohomology into a Hermitian space of signature GG, where G is the genus of the curve. And this eigenspace is some piece of that, and it has its own Hermitian metric on it. So you can ask, what's the signature of the intersection form restricted to this piece of the homology? And the answer is given by, there's a nice sort of rule of thumb to give the answer, which is you say, well, there's 4 points in the plane, so you draw 4 points equally spaced around the circle, put them at the 4th roots of unity. And then you say, I have a 718 here, so you draw 718 on the circle. And then you draw the line from 0 through 718. And the signature is the number of points above the line, comma, the number of points below the line. So the signature turns out to be 1, 2. So in other words, this is isomorphic to a 3-dimensional complex space with a natural Hermitian form on it of signature 1, 2. That should already be starting to make you think of SU1, 2. And so now here's the map. You simply send BI, the configuration of points, to the corresponding positive line in C1, 2. The space of positive lines in C1, 2 is a model for complex hyperbolic 2 space. And so that gives a local map from the configuration of 5 points on the sphere to complex hyperbolic space. It turns out to be a local homeomorphism. Pull back the metric. That endows the moduli space of 5 points on the sphere with a complex hyperbolic metric. Okay, now, and by the way, one of the reasons I like this example is because all these weights 7 are the same. You actually get a corresponding representation of the braid group on 4 strands into U12. And this turns out to be a special case of the Borel representations of the braid group. Okay, so now we can ask, what is the volume of moduli space in this metric? And here's the answer. So the complex hyperbolic volume of moduli space in the metric I just defined is, well, and then there's some formula. So in this formula, there's a constant, which is sort of the standard constant in Gauss-Bonnet. And then there's a sum over all partitions of the integers from 1 up to n. And then for each partition, there's a product over the blocks in the partition. And you have to sum the weights over the elements of this block. If the sum comes out to be more than 1, you set this equal to 0, et cetera. Okay, so there's a formula for the volume. And this is just explaining what the formula is. And I should say that this formula was derived in special cases by other different and also very interesting methods by Parker and Sauter. Okay, so what I'd like to do is explain where this formula comes from, why it's useful, and resolve the paradox of the fact that I'm computing the hyperbolic volume of something that doesn't have a hyperbolic metric. Okay, so here by the way, this is an application of this formula. So there were 94 orbifolds that were discovered by Deline and Mostow that are obtained by choosing particular values of these mu i's. For those mu i's, the holonomy of this complex structure gives a lattice of this complex hyperbolic structure gives a lattice in U1n for n equals 1 and 2. Well, actually for many, sorry, not just for 1 and 2. And there's a number which you have to compute, which morally plays the role of the Euler characteristic. And so the volumes of all of these beautiful orbifolds are tabulated in this table. Well, that's one of the applications of the formula. So now we come to sort of the main point that Thurston contributed. So let me tell you about cone manifolds. So suppose you're given a bunch of triangles in the plane, and you glue them together along their edges whenever the edges happen to have equal length, glue them together in pairs. Then you get something that looks like a surface, but the total angle around the vertices might not be 2 pi. So it has some curvature potentially along the zero skeleton after you've glued it up. So in the same way, you could take some spherical polyhedra of dimension 3, glue them together along their 2-dimensional faces. If some of the 2-dimensional faces happen to be isometric, glue them together in pairs. When you assemble this object, you might get something that looks somewhat like a manifold. It has a metric of constant curvature plus 1 on an open dense set, but now along the 1 skeleton and the 0 skeleton, there will be various kinds of curvature. So these more general objects are examples of cone manifolds. There's a version of this idea of a cone manifold in the complex hyperbolic case. Now, I should caution you that I'm deliberately misleading you about the simplicity of this idea. And the way I'm misleading you is this. In complex hyperbolic 2 space, there are no hypersurfaces that are totally geodesic. So there's no polyhedra with these top dimensional faces along which you can glue. So a hyperbolic cone manifold, whatever it is, it can't be described quite by saying you glue polyhedra together along geodesic faces, because there are no such faces. In the Riemannian case, things are even worse. Nevertheless, there's a good and beautiful definition of a Riemannian cone manifold. And what Thurston showed is that, well, when you take the metric I just described on the moduli space of endpoints on the sphere, the metric which depends on the choice of weights on the points, first, it's almost never a complete metric. That resolves the contradiction. To be a complex hyperbolic manifold, it would have to be complete. It's almost never complete, but its metric completion is a cone manifold. And this result holds no matter what the weights are. It holds, for example, even for real values of the weights. And now we can turn to the problem of computing the volume. And all we need now to compute the volume is the following. We need a formula, a Gauss-Bonnet formula for the volume of a cone manifold. Because this object is now complete, and it's even typically compact. And so you would expect that the complex hyperbolic volume of this closure is, in fact, proportional to its Euler characteristic. And indeed, that is the case. On the other hand, the original moduli space it has full measure. So you're just computing the volume of M0n when you do that. So the Euler characteristic of the completion can be used to compute the volume of the interior, and here's the resulting formula. So this is a version of the Gauss-Bonnet formula for cone manifolds. And what it says is, well, you take the usual Gauss-Bonnet integrand, and you integrate it over the top dimensional part of the cone manifold, and it's given by an Euler characteristic. Now, what is the Euler characteristic? Well, it turns out that any cone manifold is naturally stratified, and each of the strata is, in fact, totally geodesic for the stratified Riemannian metric on the manifold. And so there's a sum over the strata of the manifold, and then you just take the ordinary Euler characteristics of the strata. Now, if this were an actual manifold, the Euler characteristic would just be the sum of the Euler characteristics of its strata. But since it's a cone manifold, there's a sort of a defect. That is, along each of these strata, you can take the volume of a sphere, and you can compare it to the volume of the sphere in a manifold. And they grow, one will be proportional to the other by a constant. That constant is a measure of the cone angle along that stratum, and that's this constant theta appearing here. Okay, so there's a formula there's a version of the Gauss-Bonnet formula for cone manifolds, and it's simply what you would guess it would be. So maybe I'll say just a word about the history of this. So Capes and Moeller sent me a paper in 2012 that introduced a very interesting invariance that I'm going to allude to. And I thought, well, there should be a simpler invariant where you just use the Gauss-Bonnet formula. And so I wrote down this formula, and I computed it in the Deligne and Mostow examples. And then it took a half year to prove that this formula was correct. So I went to the library, and I looked up Gauss-Bonnet theorem for cone manifolds, and it didn't exist in the literature. So let me explain how this formula can be proved, and how, in fact, the key ideas in the proof are already in the literature, but they're in a sort of classical literature that's been largely superseded in modern thought. So, but first, let me use it to explain the volume formula I gave earlier. So the volume we wanted to calculate is now expressed as a sum of Euler characteristics and cone angles. Here was the formula that I wrote down before. Now you can recognize the pieces. This term here is the Euler characteristic of a stratum. And you'll notice that this looks like the Euler characteristic of a moduli space with p points. This term here is the cone angle transverse to that stratum. And what's happening is that when you compactify moduli space, all that's going to happen is that certain collisions between points will be allowed. For example, the point with weight 7/18 and 7/18 can collide to produce a point with weight 14/18. And so the cone manifolds, the polyhedra with 4 points on them with a new set of weights arise in the compactification of the cone manifold for these original weights. And so these strata are just lower dimensional moduli spaces, and then some function of the weights determines how they should be counted, what their transverse angle is. So I'm just saying this collision produces a stratum isomorphic to M04, which is one of these terms here. And there is no collision possible, by the way, if the sum of the weights is bigger than 1. So for example, 3 of these 7s cannot collide because that would give 21, which is bigger than 18. Okay, so let me just say a few words about a proof of the Gauss-Bonnet theorem in this setting. So the proof I know relies on this beautiful result of Allendorfer and Weil, in which they computed the Euler characteristic of an object that's almost never studied these days, called a compact Riemannian polyhedron. So it's like a polyhedron, but everything is curved. And the formula involves the usual Gauss-Bonnet integrand here, and then some other terms here which are integrated over the boundary facets. And then there's the outer angles along these facets play a crucial role. And so let me just give you a glimpse of what the terms are like in this formula. This is the traditional Gauss-Bonnet term, which involves just the Riemann curvature tensor along the interior of the manifold. And that's sort of the intrinsic curvature. And then in the second part, there's something that depends on the choice of a point on the boundary plus a vector in the dual normal cone to that point. And that is a combination of the Riemannian curvature and the second fundamental form along that piece of the boundary. So anyway, there's this beautiful formula due to Allendorfer and Weil. Why did Allendorfer and Weil prove this formula? So what happened is that Allendorfer had proved the expected Gauss-Bonnet theorem for compact Riemannian manifolds that can be embedded in Euclidean space. At this time, nobody knew whether or not every manifold could be embedded in Euclidean space. And they observed that once you have that, you can just chop your manifold up into pieces. Small pieces are known to embed in Euclidean space. And so if you have a suitable formula for polyhedra, then you can sum up all the pieces and get standard Gauss-Bonnet. So without having Nash's theorem available, Allendorfer and Weil actually gave the first proof of the Gauss-Bonnet theorem for closed manifolds. But they did it by chopping into pieces. And so along the way, they proved this beautiful theorem for a polyhedra. A year or two later, Chern gave his beautiful intrinsic proof, which has nothing to do with embeddings into Euclidean space and doesn't involve any chopping. And this result was largely forgotten, as far as I can tell, looking in math reviews at the number of times it was cited. But it's exactly what you need to prove Gauss-Bonnet for a cone manifold, because what you want to do is cut your cone manifold into pieces, into polyhedra, where the facets of the polyhedra run along these different strata. And let me just mention that this formula of Allendorfer and Weil is extremely natural, and it comes from another nice formula due to Weil, which records the volume of a tubular neighborhood of a manifold that's isometrically embedded in Euclidean space. And this can be extended to a polyhedron, and that's what Allendorfer and Weil did. OK. So in the remaining 6 minutes, let me describe the motivation for computing this volume formula. So in fact, Satake proved a Gauss-Bonnet theorem for orbifolds. And if one were only interested in computing the volumes of complex hyperbolic orbifolds, such as these beautiful 94 examples discovered by Deligne and Mostow, one could do it by computing the Euler characteristic and then applying Satake's theorem. But there's a reason why I really wanted to be able to do cone manifolds as well. And the reason is there's the following remarkable type of example. So take the group of isometries of the hyperbolic plane generated by reflections in the sides of an ideal pentagon, a regular pentagon. Okay, so the vertices of this pentagon are at the fifth roots of unity. Now, there's a Galois automorphism of Q adjoint a fifth root of unity that sends the fifth root of unity to its square. And if you were to redraw this figure after applying that automorphism, then 1 would be connected to zeta squared, then zeta to the fourth, then zeta, and then zeta cubed. And so this figure would go over to a regular star. And then you could take the group generated by reflections in the sides of this regular star, and that would give a reflection group which is almost as good as this one. The difference is this one is badly indiscrete. So we have a discrete group here, and we have an indiscrete cousin here that's obtained from it by Galois conjugation. But there's more to the picture. There's a beautiful holomorphic map which conjugates the discrete action on one side to the indiscrete action on the other side. And this map is simply obtained by using a mild generalization of the Riemann mapping theorem that gives you a conformal map from this pentagon to this star. The map has a critical point at the origin. It's branched over the origin here. Once you have that map, you can just develop it by Schwartz reflection to get a map defined on the whole disk here, whose image commutes with this indiscrete, the action of this intertwines gamma with this indiscrete group gamma prime on the other side. Okay, now here's the question I would like to ask in this setting. This map is certainly a contraction for the hyperbolic metric, as is any map by the Schwartz lemma. Here's a finite-sided fundamental domain. I can ask, what's the average contraction of this mapping? Well, let's say the contraction of volume. So what is the average value of f prime squared in the hyperbolic metric? Well, the answer is easy. You see, this map, this group here defines a hyperbolic orbifold with, which is an example of a cone manifold, but because I have integers here, it's of a special type that corresponds to a discrete group. There's a corresponding cone manifold on this side whose holonomy gives this indiscrete group gamma prime. And the fact that it's this Galois conjugation can be seen here in the fact that 5 was replaced by 5 halves. So at this vertex, we have a cone manifold that's not locally modeled by the quotient of a hyperbolic plane by a finite group, but it's a cone manifold in the sense of Thurston. And what is our map? Our map is just the identity map from this triply punctured sphere to this triply punctured sphere. And so what is the average value of the derivative squared? It's the ratio of the volume of this orbifold to the volume of this cone manifold. And that's in turn the ratio of their Euler characteristics. So the Euler characteristic of the triply punctured sphere is -1. Then you put in a half of a point and a fifth of a point to make up for these things. You get -3/10. Here, the Euler characteristic is -1. You put in a half plus 2/5, and you get -1/10. So this guy is 3 times bigger than this guy, and so the average value of the derivative is 1/3. Capes and Muller's observation is that this number, 1/3, is an invariant of the commensurability class of the group gamma. And so that observation can be applied, for example, to our 7778 moduli space. So what would happen if we were to change our choice of the 18th root of unity? This is a primitive 18th root of unity. Suppose we were to change this from zeta to the -7 to zeta to the -5. That would correspond to the moduli space for a new set of weights on these points. And the signature of that, the corresponding moduli space, would still be 1, 2, because of this mnemonic I just discussed. There's still 1 point above and 2 points below. So this object gives rise to a complex hyperbolic space, as does this. Moreover, there's a map between them. Sorry, let me bring them both into play. So on this side, we have a complex hyperbolic orbifold. On this side, we only have a complex hyperbolic manifold. But they're both obtained by compactifying the moduli space of 5 points on the sphere. And so because of that, it turns out there's a holomorphic map from this orbifold to this cone manifold. And an invariant of that map is its volume contraction, which is again, simply a ratio of Euler characteristics. Now, where do these examples come from, and why are they interesting? They're interesting because of the fact that when you have 2 different Galois conjugate models for the same group, both of which lie in non-compact models of the Lie group, that means the lattice is a non-arithmetic lattice. If all the Galois conjugate factors were compact, we would have the standard construction of an arithmetic group. But if there's the corresponding different forms of the group have at least 2 compact factors, then this lattice can't possibly be arithmetic. And so this was one of the motivations for Deligne and Mostow's work, using this construction of complex hyperbolic metrics on moduli spaces. They found examples that were orbifolds, but which were not arithmetic. And coming back to Mostow rigidity, one of the main remaining open questions is, to what extent do we have the rigidity, superrigidity of Margulis in the setting of complex hyperbolic geometry? And the existence of these non-arithmetic lattices violates the arithmeticity that one sees in higher rank due to Margulis. OK, so let me just complete this example and finish with an open question. So what Capes and Muller, slightly modified by my idea of using volume, observed is that these volume ratios are the same for all the subgroups of finite index in gamma. In other words, they're commensurability invariants of these groups. And there are 16 non-arithmetic lattices arising from these moduli spaces. Using this invariant, you can see they fall into 9 commensurability classes. So these are the angles you put on the vertices of the 5 or 6 times punctured sphere. There's the example we've been discussing. The volume ratio turns out to be a 16th. It's the same invariant as for these weights, and these groups turn out to be commensurable. Of course, non-arithmetic groups, commensurable cousins, are also non-arithmetic. So you don't want to find the cousins of the same group. That's not a new example. You want to know how many of these examples are really different from one another. And these invariants cleanly distinguish all of the known non-arithmetic examples. OK, so that was my motivation. That's the application. But of course, this is only the tip of the iceberg. This simply draws attention to how little we know in this setting. So let me just conclude with the following 2 challenges. The first challenge is to find even one non-arithmetic example in the setting of 4 complex dimensions. And the second is to determine whether or not there's only finitely many non-arithmetic lattices up to commensurability in the 2- and 3-dimensional cases where they've been constructed. OK, so I'll stop there. Some are. Yeah. It's still interesting. Some are and some aren't. Both are possible.
Now, this story of putting the weights on this marked point, does that work for higher genus marked moduli space of MGN?
So the problem is, so yes and no. The problem is constructing a canonical covering. So I already broke a little bit of symmetry by putting one point at infinity. So the point is, you have to have a map from the fundamental group of your Riemann surface minus these end points to, say, Z mod 18. Right? So for the sphere, there's only one map which sends a peripheral loop around each puncture to the generator. That's why we have hyperelliptic curves canonically attached to n tuples of points, even numbers of points. On a Riemann surface, there's more choices for that map, but it just has to do with homology with coefficients in Z mod n. So one can make a similar construction.
What do you know about the homology of these very special groups?
So these groups are all quotients of the Bragg group. And the Bragg group's homology has been very much investigated. What's happening here is that when you introduce a cone locus where some points collide together, you're adding, there's a Dane twist in the Bragg group, or more properly in the mapping class group, around a loop that encloses those points. And when you add a cone locus or an orbifold locus, you're introducing the relation that an nth power of that loop becomes the identity. And as far as I know, the cohomology of those quotients has not been computed.
Not even by supercomputing?
Not even by super mathematicians. As far as I know.
Is it known like which one has a minimal volume among these lattices?
Well, so, okay, so, oh yeah, sure. So the minimal examples are arithmetic. Yeah, they're very beautiful. And for example, there's a whole development in that area that Ruth Kellerhouse and her school have pursued. But from my perspective, what's truly challenging is finding new constructions of these lattices. And you have the sense that the only limitation is our mathematical imagination. That is, if you could just think of a way of doing this. By the way, Thurston's version of this would be the following. When you have, say, an octagon in the plane, not a regular one with all angles 135 degrees, the shapes of these octagons gives you a complex hyperbolic manifold. And I remember walking out of class one day saying, I'm mystified by what you're doing. And he said, well, look, this octagon sits in a square, right? So it's like the sides of the squares are AB. And, but then you have to get rid of these corners, which have sides A, B, C, and D. So the area is AB minus A squared minus B squared minus C squared minus D squared. And that's a form of signature 1. How many variables do I have? 6, 1, 5. And that's the proof that this has a complex hyperbolic structure, is that the area of a polygon with its corners off gives this quadratic form. So the quadratic form, at the end of the day, is the area of the polygon. And so, who knows whether or not there's a similar elementary construction just waiting to be discovered.